Okay, in this problem, we are once again solving for bearing size. This time there's a little bit of statics involved, and we've got to make some assumptions about the actual design intent in the shaft itself. I've already run through the statics and determined that the bearing at B over here has the higher load. It's got about 92.86 pounds in it, which is about 413.2 newtons. Now the shaft, we've got this one specification that the shaft should fall in the 1.5 to 2 inch diameter range. So we got to keep that in mind as we're choosing bearings. We may end up with a bearing that's bigger than we need to be in order to meet that range. Because for the time being, I am forming the assumption down here that a constant diameter shaft all the way from bearing A to bearing B is desired. We may find that that's not the most efficient design, but from a manufacturing standpoint, it'd be very easy to put together. This is a ball bearing, so A is going to be 3, and we are going to assume that it is non-Timken. So with FD identified as 413.2, the desired life and RPM specified, we can calculate a C10 value and then see where we're at in the bearing tables. So for that, we're going to have, of course, we've seen various forms of this basic relationship, but the one that works really nicely here when you're basing something, choosing a catalog load rating, is to have the life in hours along with the RPM and the 60 for conversion, and then have the rated life in cycles, because we know for non-Timken bearings that's 1 times 10 to the 6. That way we can just plug numbers straight in. And plugging numbers in, we'll have 413.2, 5,000 hours, an RPM of 400, the 60 conversion, 10 to the 6 for LR, and then A we've already said was 3. That gives a catalog dynamic load rating of 2.038 kilonewtons. That's pretty small. And I don't have the catalog to pull up right here, but if you look at table 11.2 in Shigley, you'll see that that is below the C10 rating of the smallest bearing in that table, which means that according to these specifications, literally any bearing in that table would actually work. And that's according to the life requirement of the bearing. But we do have another specification for that size range. We wanted the shaft to be 1.5 to 2.0 inches in diameter. Converting that to millimeter, we have about 38 and about 51 millimeters. So the smallest bearing in the table that would fit that range is the 40 millimeter. Now we'll produce a shaft which is just over 1.5 inches. And I am going back, I've got a problem that specified a shaft in imperial units, and I'm solving for metric bearings. I can look up imperial bearings and solve it that way, but the math is exactly the same. So we're just kind of converting this problem into metric shaft design, I suppose. So 40 millimeter is the smallest that fits the range. Relative to the problem statement, that is essentially what is being asked, is what bearing in that table range will work for this range of shaft sizes. Makes the most sense. As long as the shaft, minimizing the shaft will reduce material costs there, so going with the smallest bearing possible from your family of bearings makes sense in this case. But what we can do, since we've pulled that bearing, we can grab its C10 load, which is 30.7 kilonewtons, and actually see what the life is going to be. Again, this is not required, and we know the life is going to exceed 5,000 hours at 400 RPMs, but we can take a look and see what it actually is. So rearranging the life-force relationship one more time, we've got C10 divided by FD, which I'm going to express in kilonewtons, a very small value. That is going to give me life of the design in hours as 17.09 e to the 6 hours. We're looking for a life of 5,000 hours, and we got many times that. So for this shaft design, the mechanical specifications that it fall within that diameter range, that just tells us that any bearing we choose out of the 200 series is going to be strong enough. So if you wanted to come back on the ends of the shaft and machine out a step down to a smaller size in order to use a smaller bearing, in theory that would work fine for this problem. And there's advantages to that too, because that gives you a seat to press the bearing up against, which might be advantageous. But ultimately, the solution to the problem, in the sense of the actual context of the problem, the best bet out of the 200 series bearings is that 40 millimeter.